All right, so Unit 6, and honestly a lot of the chemistry we'll probably start out with next block. This is going to be all about the mole, okay? So let's talk about the mole. So today you're going to learn how the mole of a chemical relates to formulas, reactions, number of molecules. A mole is a very useful unit in chemistry. It makes it so that we have something actually tangible to work with. Okay, I highly suggest in lesson 6.02 on page 8 and 9, there's a couple of sample calculations in there. You have to click through some things to see all of it, but I highly suggest doing that. It shows you how you can apply dimensional analysis to this. And in future videos, we'll do practice with that too. Okay, so we've talked about atoms before. We've kind of talked about their size. We know we can't see them, okay? So a mole is a count, a package, a standard amount of atoms that when you have a mole of atoms, it's actually something you can measure, see, work with, okay? So it's kind of like the idea, when you say you have a dozen donuts, you know you have 12 donuts. When you say you have a mole of carbon, that correlates to a very specific number, okay? And that number is huge, okay? It's 6.022 times 10 to the 23rd. So if you have a mole of something, you have 6.022 times 10 to the 23rd of that something, okay? This number was formulated, calculated, figured out by Amadeus Avogadro. So sometimes you'll see it referred to as Avogadro's number, okay? But just to try to give you some ideas about how huge this number is, okay? If you were to count all the people on Earth, there's 7 point something billion, all right? Billion is 10 to the 9th. And we're dealing with 10 to the 23rd. If you counted every single penny on the earth, which there's considerably more than there are people, you still wouldn't get anywhere near a mole. The stars in the Milky Way, there are definitely trillions of stars in the Milky Way, but we still aren't getting to that point of having a mole of stars. The only thing that might get even close to that number would be if you counted all the stars in the entire universe. Okay? So I mean, this number, it's hard to wrap your head around because it's so big. It's hard to imagine, having anything related to that number, except when we deal with atoms, because atoms are so tiny, the mole is actually a really useful number. Okay, a gallon of water has approximately 210 moles of water molecules. Okay, now you can actually see water, and you could even probably split it up into 210 separate, drops or pores, and see the physical amount of one mole. Okay. So, the mole is useful for counting atoms and dealing with an amount of atoms that we can actually see and work with. Okay, so whenever you're dealing with an experiment in chemistry and things like that, you're working with moles of copper, moles of hydrogen, moles of whatever, because we can't deal with just a single atom. It's too tiny. We can't see it. We can't do anything with it. So, moles of singular atoms, so an element that forms in a singular atom amount, 1 mole will always be 6.022 times 10 to the 23rd. Something that you will see, and generally speaking, the formula is given to you, all right? But if you're dealing with a few elements that form diatomic molecules, meaning you don't find a single oxygen atom alone by itself. Okay, when we're dealing with elemental oxygen gas, all of the atoms inside the oxygen gas are in pairs. Okay? So a lot of times if you have a mole of oxygen gas, you actually have twice as many atoms than if you had, say, a mole of iron. Okay? So just something to keep in mind. But for all of those diatomic elements, 1 mole of that particular, and these are almost all gases, but 1 mole of that particular element, so a mole of the molecules, will have 1.204 times 10 to the 24th. Sorry, that is a typo. 24th atoms. So the formulas give you a way of counting the moles when you are dealing with something that's not just in its elemental form. Okay? So if you had, with oxygen gas, to figure out how many atoms are in there, you took that subscript 2 and multiplied it by 6.022 times 10 to the 23rd. Okay? So you took that 2 times the 6.022 times 10 to the 23rd, and that became 1.204 times 10 to the 24th. Okay? You can do that same sort of thing with the individual elements in a compound. Okay? So if you have 1 mole of this compound, copper sulfate, and you wanted to know how many moles of each individual atom you had, you'd take the subscripts and multiply it by 6.022 times 10 to the 23rd. Okay? Because I know that if I have a mole of copper sulfate, I have a mole of copper sulfate molecules. Okay? Which means that every single one of those molecules has 1 copper in them, which means I will have 1 mole of copper. All right? Also, since I have a mole of copper sulfate molecules and each molecule only has 1 sulfur in it, I'm going to have 1 mole of sulfur. Okay? But oxygen, on the other hand, because of that subscript 4, in every molecule of copper sulfate, I have 4 oxygens. So I'm going to have 4 times the 1 mole, or 4 moles of oxygen. Okay? Another way you can see moles is in in a reaction equation. Those coefficients give you a ratio of moles. Okay, so like the iron chloride and the iron hydroxide have no number in there, so that would be 1. All right. So if you have 1 mole of iron chloride, how many moles of sodium hydroxide do you need? Okay, and that's where that 3 comes from. For every mole of iron chloride, we need 3 moles NaOH. Okay, and then for 1 mole of iron chloride, how many moles of sodium chloride do you make? Again, it's 1 and 3, so that's 3 times more, so you'd make 3 moles sodium chloride. Okay, and then if you have 1 mole of iron chloride, how many moles of chlorine atoms do you need? So again, if you look at this formula here, if I know I have a mole of the iron chloride, right, so I have a mole of iron chloride molecules, and I know every molecule has 3 chlorines in them, then I'm going to have 3 moles of chlorine atoms. All right? I hope this is making sense. If it's not, please ask questions, because this is vital to understanding Unit 6 and to continuing with the chemistry class. So, especially since we're not doing this in a live class, so I won't have interaction with you, I'd really appreciate you answering these questions, emailing me your answers. That way I get a feel for how you're doing, and I will throw some extra credit your way if you do that.